All right, guys, today's section 10.6, kind of circling back, but again, we're very much in our finals review. We're in our performance review aspect of the test. You may recall when we finished up the Chapter 10 test with conic sections and all of that, again, that test was 10.0 through 10.4, and then we jumped into section 10.7. So we had a conversation back then, again, albeit a couple weeks ago, we had a conversation saying that no, we're not completely skipping section 10.5 and 10. We are completely skipping 10.5, but we are not completely skipping section 10.6. It's more of a temporary thing. To me, in my opinion, and I think that you'll agree with me once we get through this stuff, it just doesn't fit really well with the conic sections, and it doesn't fit really well with the polar graphing. It's just kind of there, and there's a lot of value in it. Please don't get me wrong. I'm not saying that this stupid junk that we have to talk like. No, that's not it. It's just that it's an important concept. That it's not big enough to be its own chapter, but it's not going to again mesh well with any of the others. So I've handled this many different ways over the years, but I don't know, the last 3 or 4 we've handled it this way to where again conic sections, test over that, move into the polar, quiz over that. And then we're ready to start talking about finals review, so this just kind of gets lumped into the finals review. And it's gone pretty well. A lot of years previously, the textbook puts this in between conics and polar, so let's put it in between conics. And then sadly, a lot of people forgot about it. So again, you guys know me. I'm the person that generally does not feel the least bit confident or comfortable saying this is easy, this is hard. Again, I usually don't like to get into that, but I would say I would report back that most students they generally say that the question dealing with parametric equations on the final exam is that was probably the easiest question. That's what a lot of students will say. That physics people, have you guys talked parametric equations? Is that something that has come up? I'm seeing a lot of heads shaking no. Okay, so never mind. But we could, in all seriousness, we could spend weeks, maybe a month, talking about parametric equations. There's a lot there if we really wanted to go down that rabbit hole. There is a lot that could be done with this. But with what we need to do, it's really not getting into the crazy abstract word problems. We're getting into the, literally what's parametric equation, and how would we sketch its graph. So to really kind of sift through all that garbage that frankly we don't care about, if we're to talk about parametric, just that word, any other kind of subwords or root words, better way to say that this relates back to that you're thinking? What do you got, Vincent? Exactly. So parametric, it kind of relates back to the word parameter. So basically, again, I'm talking like in extreme generalities here. If we're talking about parametric equations, we're talking about equations with parameters. That's pretty much it. Now, for us, there are different parameters out there, but for us, we're going to be using time, t, as the parameter. And like I said, there are different parameters that are out there. There are different ways that we could structure equations. And if you stay in this math game for a long time, again, into your college experience, you will see more with parametric equations, and you will get into having other parameters, in addition to time, or not only time, but also, there's other types of problems that you could get into. Like I described it earlier, you could go down that rabbit hole, and there's a lot there. Okay. The good news, though, is that really the structure of these problems is going to look very similar to what we've been using since pre-algebra, algebra 1. We just need to, here's what we know, here's how we can apply. It's really what we need to talk about. All right? But again, if you need it for reference, this is from section 10.6 in your textbook. We just have a few things we want to talk about here today. So, like many of the other concepts, especially new concepts in pre-calculus all year, again, like a broken record, been saying it all along, that this is going to initially look much harder than it really is. Okay, it's going to look to be more complicated than reality here. Okay, But I mentioned a few seconds ago now, that parametric equations, they're just equations with parameters. And I don't want to just blow by that. When you hear the word parameters, like, what does that mean? What are there some other similar words that maybe come to mind? What are you thinking about when you think parameters? Limitations, I like that one. Good. Anybody else? Parameters. What does that mean? Sorry? A value that can change. And it can change, but don't we have, using Laura's word, don't we have limitations then? Like, it has to stay between this and this sort of thing? Yeah, but Ben's absolutely right. That we have a variable that's going to be changing. I mean, that's what makes this interesting. It's not stationary. There's gonna be movement involved. That maybe t is this, maybe t is this, maybe t is this, but there's going to be limits to that. Again, the word that comes to mind for me, I don't know, I'm sorry if I'm cutting anybody off. If you're thinking the same thing, I'm just not giving you a chance to say it. But to me, the word that comes to mind when I think about parameters is boundaries. Okay, we're going to have a lower bound, we're going to have an upper bound. We're going to stay between there, but we're going to have an infinite number of possibilities, technically, between your boundaries, okay? Within your parameters, if you will. All right? So that's what we're going to be talking about here and now. So the definition, I'm sorry, but yeah, I am just going to read this off. We say that the values of x and y, and again, I do want to be very clear. We've been talking about polar. This is the one spot that I'm a little, maybe we should talk about this before polar, maybe not. But when we're thinking about x and y, we're thinking not about the polar system, but the rectangular system again. Okay? So we've got the values of x and y. They're going to be dependent upon a third variable. For us in this class, it's always going to be t. Time is going to be that third variable. Okay? So our equations that we're going to be working with here, the first equation, we're going to say that x is merely equal to f of t, and y is going to be equal to some other function g of t. Okay? All that means, again, this looks super fancy. All that means is that if we need to figure out what x is, all right, what's my little equation? What do we know time is? Oh, time is 0. We plug that in and we see what now after 5 seconds, we put t in place and we see where we're at. After 30 seconds, we put t in place and we see where we're at. Okay? That's all that we're doing. We can do that to figure out x. We can do that to figure out y. And once we've figured out x and y for the same t, the same time value, now we have a coordinate. Does that make sense? You do that enough times, you could start to see what the graph is going to look like, what the curve is going to look like. Okay, so in a nutshell, that's all that we're doing. I apologize in advance if you're a person who does not like tedious work, tedious but simple work. That's really what this is. We're going to be building T-charts, plotting points, drawing curves in between the points. That's parametric equations here in pre-calc. Okay, so we're going to say that the set of ordered pairs, f of t, g of t, which remember it's just x, y, all of those points, they're going to create what we call a plane curve. Again, t is the parameter. All right? So, here's the deal. And again, we are going to go, like I said, we're not going all the way down the rabbit hole, but we are going to, kind of look into, some of the possibilities, even though that's not exactly what we're doing. Definitely not what we're doing on Friday's test. But, again, I do think that it's important that in future classes, should these show up, is anybody doing physics 2 in here? AP physics 2? Like currently, are you doing it? I want to say that you get into parametric equations in physics 2. Again, obviously, I'm not Mr. Redding. He would be able to answer that question a heck of a lot better than I could. But I feel like that's something that I've had seniors taking pre-calc who are simultaneously taking physics 2, and they're like, oh, yeah, we've done stuff like this. But I could be misremembering. All right? So here's the long and the short of it, quite honestly. I think this is my best attempt to really sum this up in one sentence, what we're going to be attempting to talk about. Not only the where, meaning how far out x, how far up y, but also the when. So again, it's not just where is this point located, but when is it going to be located there? Because we're talking about a moving target, and after 3 seconds it's here, but after 5 seconds it's there, and after 10 seconds it's here. How can we map that out is really what we want to do. Okay, so I've got an example here. I think that we all could probably relate to this. What if we were driving to Lincoln? Okay, Lincoln is directly southwest of here. So We left from PLHS. We're driving to Lincoln. We said here in my made-up example that we're driving at a rate of 75 miles per hour. The origin of your trip is PLHS. How far west and how far south are you after 30 minutes? Okay. So what that means is that we're going to leave from high school, drive to Lincoln. Use easy numbers. 50 miles, we'll say, to Lincoln. It's probably a little bit more than that, but let's just say that it's 50 miles to Lincoln. Okay. If we left from here. So, okay, it's probably more. It's definitely more than that. But let's say 60 miles. How about that? I think that's probably a little bit more in the ballpark. So if Lincoln is 60 miles from here, obviously it depends on which part of the city of Lincoln you're driving to. It's a big city, but if you leave from here 60 miles and we're in Lincoln, we're traveling at 75 miles per hour. I don't know, what is it? About 45 minutes. We would think that it's going to take us to get there, give or take. So do we agree that if it's going to take us from the high school to Lincoln, it's going to take 45 minutes. After 30 minutes, we're not there, correct? We're driving along. After 30 minutes, maybe we're here after 30 minutes. Does that make sense? Now, if we're on an XY rectangular coordinate plane, we left from the high school, and we call that the origin 0, 0. Lincoln is, I don't know, -60, -60, something like that. Could we figure out where we are location-wise? What's X, what's Y after 30 minutes? Sure. If we have the equations, if we have the functions to back it up, we can do that. Okay? What if we changed our mind and said, no, sorry, you misunderstood me. I didn't mean 30 minutes. I meant 13 minutes. Where we could figure that out too, right? Oh, again, change my mind, 33 minutes. Again, we could do this for any value of t, as long as we know the function. Does that make sense? Which we don't know the function because we just made it up. Okay? But those functions, that would build what we call that parametric equation. All right? Again, it's parametric because it not only talks about your position, like your location, what's X, what's Y, but at a specific time, that's how we get there. That's what makes it, that's what kind of upgrades it to being a parametric equation. All right? So I tried to come up with some other parametric equation type examples. The first one was me obnoxiously being as ridiculous as I could possibly think. Imagine that you drop a water balloon on a person who's riding in a roller coaster and you drop it from a moving helicopter. Okay? So like think about that. A helicopter's flying over an amusement park. Somebody's going on a roller coaster and you drop a water balloon. Do you agree that would be an incredibly lucky hit? Yeah, like that, it would be incredibly unlikely that you just drop a water balloon and you happen to hit somebody going on the roller coaster. Because they're moving at a very fast rate. Your helicopter is moving in some opposite direction, most likely. You drop, again, now you got wind, you got all these other things, but we understand that parametric equations could be utilized to figure out more precisely where and how that drop would happen, right? Again, it'd still be a lucky shot. I don't know why anybody would want to do this, but throwing snowballs at a moving car, okay? A little bit more, I don't know, I guess more legal way of looking at it. Now a quarterback throwing to a receiver, okay? Quarterback's not going to throw to where the guy is. He's going to throw to where he's going to be. Again, if he's running to a spot, again, they got to be on the same page. The quarterback has to know, okay, how fast is this guy? When is he going to be there? I'm going to throw it precisely here, and the timing should work out. Okay, so that's, again, keyword being timing when we talk about these parametric equations. Missile hitting a moving plane, a torpedo hitting a ship. If you're hunting or trap shooting or something like that, again, basically what we're getting at, dodgeball, we say, yeah, if you're stationary, you probably suck at dodgeball. Again, you're going to be moving around. You have to hit moving targets. And that's what these parametric equations are really going to be emphasizing, is we have moving targets. They're moving at certain rates, so at different times, people are going to be, or things, objects are going to be at different locations. Okay? So that's what we're talking about. No, we're not getting into all of these crazy word problems, but that's what we're saying is that we could. All right? So this is more likely what we need to be able to do. This is what we're going to see on Friday. Let me stop video here.